make just one quick announcement. We have a distinguished lecturer coming up June 2nd, and he's going to be speaking on biomedical imaging. Signal Processing Society is sponsoring him, so we're pretty excited about that. Be looking forward to that. And that invite will be coming out in the next few weeks. But tonight, I want to introduce Kevin Scow. Kevin is the lead forecaster with the National Weather Service in LaCrosse and has been there has worked for the National Weather Service for 16 years. He grew up in the Twin Cities and graduated from the University of North Dakota with a bachelor's in atmospheric sciences. He began his weather service career at the Anchorage, Alaska office in 2009 before moving to Des Moines in 2011. He then worked at the Topeka, Kansas office from 2016 to 2021 before moving to LaCrosse. His main areas of expertise involve severe weather warnings, radar interrogation, and post-event storm survey. Please, let's welcome Kevin.
All right. Thanks again for having me. Again, my talk will be focused on the National Weather Service WSR-88D radar, which has been the backbone of our radar network here in the United States for the last 35 years. So without further ado, quick basics. Hopefully this is just a review for all of you of what radar is, what radar entails. Radar itself is just an acronym for radio detection and ranging. Real basic, it just transmits, the radio receiver or antenna transmits a burst of radio waves out in a given direction. Those waves bounce off of whatever they encounter in the atmosphere, whether it's bugs, birds, airplanes, raindrops, hailstones, you name it, it bounces off that. The energy is then scattered away from that object and some of that energy is then received by the antenna back at the radar. And the properties of the radio waves are then decoded by the receiver. We can tell how far away these objects are because, of course, radio waves travel at the speed of light. We can then figure out how far away they are based on how long it takes for energy to come back, to be sent, and then return back to the radar. And of course, the WSR-88D is an acronym. We love acronyms in the National Weather Service and the government. We're full of them. So the WSR-88D stands for Weather Surveillance Radar 1988 Doppler. And we'll get into more, especially about what that Doppler aspect means here in a few slides. Currently, our radar network across the United States, we have 159 WSR-88D radars. Your closest one here to Rochester is the one located over in LaCrosse. Similar ones are located close to here in Minneapolis, Des Moines, Sioux Falls, and again, lots of other ones across the United States. When I was working in Alaska, you can see the radar network isn't quite as good down up there, just basically due to it was based upon how much the population density is and so forth. So we have very good radar coverage, especially across the eastern half of the United States. As you go more towards the western half of the United States, we have to deal with the Rocky Mountains. And so radar beams don't like to travel through rock. So we don't have very good coverage in some areas there. You'll see a lot of the radar coverage patterns are blocked by some of the mountains up there. So we put the dishes up as high as we can, but we can't quite get to all the tallest tops of the mountains and so forth. So you'll see some of that in the radar coverage patterns there. But we have very good coverage here across southern Minnesota, across southeastern Minnesota, especially as you get, again, closer to LaCrosse and Minneapolis. So a brief history of the National Weather Service radar. Again, in the 30s and 40s is when the radar technology really started to be born from the World War II, especially on the Allied side. And of course, we learned very quickly as we were trying to detect ships and aircraft that we were able to detect precipitation as well. And so right after World War II ended, the U.S. Weather Bureau at the time got its hands on a surplus Navy radar and designated it the WSR-1, Weather Surveillance Radar 1. And really through the late 40s, early 50s, they were tinkering with it, trying to figure out what would be the best antenna size, as receiver, and so forth for detecting precipitation. And through a number of different iterations, the WSR 3 and 4, these were deployed haphazardly across the country just to see what they could do. And finally, in the late 50s, early 60s, when the Weather Bureau first deployed its its first national network of radars. They were dubbed the WSR-57s. These were a S-band radar. Only were able to compute, only able to show reflectivity. And this is an example here on the right-hand side. This is one of the early images from a WSR-57. That's actually from the, I believe it's the Palm Sunday, Minneapolis tornado outbreak from 1965. So that's an example of what the early radar images used to look like. And people would, the meteorologists would have to go to the radar scope and trace out the outlines of the storm with grease pencils and trace to see how it was moving in time. And it was very rudimentary back then. We didn't have computers, of course, at that era. And this WSR-57 network would really serve as the backbone of our radar network for about 30 years. And in the 70s and 80s, we filled it in with a secondary class of radars called the WSR-74Cs. And then really in the late 80s, mid to late 80s, the Weather Service was looking for a way to upgrade this radar network. And what was born was the WSR-88D, or the NEXRAD radar network. And these were deployed primarily in the early to mid 1990s. The upgrade was complete right around 1996, 1997 or so. And this really was the first radar that was able to detect particle motion using the Doppler effect. That D in the WSR-88D, the Doppler effect, is what really made this radar a huge upgrade over the previous radar systems. And, work began right after this was done to see what could replace it in the future. And there are ideas of what can be done, but really not a whole lot has been done to explore what the future will be of this radar network. So a lot of work was done in the 2010s of improving the scanning strategies of this radar, finding new ways to look at new data, and then, of course, we'll see at the end there about what the future might hold for the 88D. But we've done a lot of upgrades to the WSR-88D over the years. The data you would see when this radar was first deployed in the early 90s is certainly nothing like you can use it for today. It's really amazing how much we've been able to use our current hardware and just improve its capabilities over time. And we've improved the product resolution over the 90s to early 2000s. We started with 4-bit data, which was really crude. You could hardly see a lot of stuff with that. And improved to 8-bit, and then eventually what we call super resolution radar imagery. That came out right before I started in the Weather Service in 2008. A big upgrade that we had in the early 2010s was called dual polarization. And I'll cover what that means here in a couple slides. So this was really a big game changer for being able to take a 3-dimensional cross section of what we're sampling in the atmosphere. And then since then, we've been trying to improve the scanning strategy of the radar to make it scan faster in the atmosphere and get that low-level information that we really need for looking for, say, tornado genesis. We've improved that with what are other acronyms down there. Again, we love acronyms. I'll explain what all of this is here in the next few slides. And then we're also trying to improve the velocity data. That's the last thing that just came out last year, was being able to improve the velocity data and being able to see that those particle motions clearer in the atmosphere. So here are just the real basic rundown of the radar components. This is using our radar here at LaCrosse. Our radar, when you go from the ground to the top of the radome, is 130 feet tall. We have a fiberglass dome that encompasses and protects a 28-foot wide antenna reflector dish on the inside. And this rotates 360 degrees on a pedestal and can rotate up and down vertically as well. So what happens is, of course, at the ground, we have our Klystron transmitter that transmits radio wave energy up through a waveguide that then goes up to the antenna, and this is then broadcast out in both a horizontal and a vertical pulse. And this is what makes dual polarization so special, because prior to 2010, what we would do is transmit those radio wave energy particles in the horizontal orientation. This is because raindrops are not circular, they're kind of hamburger shaped. And so what we tried to do when we transmitted in the horizontal orientation, we were able to see the differences in the raindrop sizes better. But what we then did is we transmitted radio wave energy in both the horizontal and then the vertical. So we split that radio wave energy right at the antenna and then broadcast it out in 2 different channels. And that's what makes dual pol special. And then that energy comes back to the radar. It is then decoded by the receiver and generated into the products that you and I use on a day-to-day basis. So here is I had to make the nerd slide, as I called this. This is all the tech specs for the WSR-88D. Again, it's an S-band radar. We'll get into more about what makes those bands special here a little later on. We vary the frequency of the radars from about 2.7 to 3 gigahertz. And the reason we vary that frequency is because we don't want to be receiving in LaCrosse the radio wave energy from Minneapolis. So we vary that frequency a little bit so we're not suddenly getting energy from a different radar we don't want to actually be looking for. So that's the reason why there's like, gosh, I don't know, 5 or 6 different frequencies we use within that spectrum. The output power is generally between 650 and 750 kilowatts based on what scanning strategies we are using. And again, because we're shifting that frequency, the wavelength we're using varies as well between 10 and 11 centimeters thereabouts. The beam width is about 1 degree thereabouts. We actually reprocess that data using the super resolution technique down to ½ degree. And the rotation rate, it varies based on the scanning strategy we're using, going anywhere from 5 to 35 degrees per second. The elevation goes from as low as -3 to 65 degrees, but we don't actually utilize all that full range, and I'll show you why we don't do that here in a little bit. The radar primarily has 2 scanning modes. We call them short pulse, and we call it long, and the other one is called long pulse. And the big difference with short pulse versus long pulse is the pulse width, of the time it takes between those pulses the radar emits. And you'll notice that with short pulse, it's a lot shorter of a duration versus long pulse. And the big difference there is with long pulse, we want to try to sample, say, snow or small drizzle drops, where we need to be able to sample the atmosphere for a longer time to be able to see that faint radio wave energy reflected back to the radar. So with short pulse, we tend to use the radar more for severe weather. It does great because we're looking for big raindrops and hail, easy to see with the radar. If it's not so easy with the radar to see, we switch it into long pulse, which then is slower to rotate and slower to sample, but you can see the minimum signal that is able to be seen is a lot better with long pulse versus short pulse. As I said, this is the WSR-88D. D is applied, it means for the Doppler shift. Again, real basic stuff here. As the object is moving towards you, the sound waves are compressed. They have a higher frequency, and therefore its sounds have a higher pitch. And we call this a positive phase shift. Whereas as the sound waves are moving away from you, they get stretched, they have a lower frequency, lower pitch, and we call this a negative phase shift. So what we run into with the radar is known as the Doppler dilemma. How many of you guys have ever heard of the Doppler dilemma before? Anyone? One, maybe, kind of, sort of? So the issue we run into with the radar is ideally we want to be able to sample as far away from the radar as we can. However, we want to also sample really high quality velocity data, but we can't have the best of both worlds there. And the reason has to do with what is known as the pulse repetition frequency, or the PRF of the radar, and which is, again, the number of pulses transmitted each second by the radar. And the range has an inverse dependence on the PRF. So basically, you know, if you wait longer, the signal can travel farther before you emit the next pulse. Whereas the best velocity data, the best, we call the Nyquist velocity, has a direct dependence on that wavelength. So if we try to scoot the PRF up, the Rmax, you'll see that you can't sample the highest quality measurements of both of those. So what we do with the radar to try and solve the Doppler dilemma, again, if you have a high PRF, you can see higher velocity values, so you can see those higher. You can be able to sample higher velocity increments before what happens, what we call velocity folding. And what happens when that happens is, you can see in this example here on the right-hand side, this is a great example of what we call aliased or folded over velocity data. The green values are where we have echoes moving towards the radar. The red values are where we have echoes moving away from the radar. And suddenly you see this really hard jump right here. And this is where the radar can't actually figure out if the signal is moving towards or away from the radar anymore. It's the velocity folded over, essentially, in the spectrum is what we called it. And so what we do to try to get around this is we do 3 main things. First of all, we actually do 2 different scans at some of the lowest elevation angles. We'll optimize one scan for reflectivity or for the range, and then we'll do a second scan optimized for velocity. That's actually what we do a lot and what helps us a lot for that. We also do flexible PRFs, so we can try to change how we're changing the pulses that are sending out from the radar to try and get that highest quality velocity data possible. And then we also have algorithms to try and decode those ranges. So if we have an example here on the bottom here, this is a great example of what's known as a first trip and a second trip radar signal. So what's happening here, you see this ring right there on the radar. The radar energy is being sent out and comes back, but before the energy out here where the number 2 is can come back to the radar. We've emitted the next pulse, and the radar doesn't know when the energy was sent. So it's seeing the energy still coming back from the area way out here up by, this is actually from the Minneapolis radar. So this is up by, say, Lake Mille Lacs. The energy is still coming back to the radar as we're sending out the next pulse, and the radar doesn't know where to put that echo. It just can't figure it out. So we have algorithms now that can help decode it. You still sometimes see this secondary ring right here where we have between the first trip and the second trip echoes. But we can see a lot better data out there beyond that first trip. So we have algorithms to help us out with the various VCPs that we use, or volume coverage patterns. And so this is the nerd, again, another nerd slide I came up with. Hopefully this is something of interest. We have 8 different PRFs that we can use on the radar. We call them 1 through 8 just to keep it simple. What's really interesting to see here are these last 2 columns. Rmax, so again, the max range that we can sample with the radar before we hit that second trip echo. And then Vmax, which is, again, the Nyquist velocity, or the highest velocity we can measure before we fold over and we can't figure out what the velocity is anymore. And you'll notice we start with PRF1, which has, the highest range. We can go to 336 kilometers. Oops. But we can only sample up to 22 knots, which is not very high, before the radar data folds over and we have to really start working hard to try to figure out what it is. And as we move that PRF up, you'll notice the range really starts to fall off all the way down to 117 kilometers for PRF 8. But the highest velocity we can then sample is 62 knots, which is much better before we start folding over. And you're going to capture a lot better detail in your velocity pattern. So I mentioned the volume coverage pattern a little bit ago. The radar just doesn't scan at the surface and be done. We want to be able to capture a 3-dimensional look at these storms. And these storms can extend up to 30, 40, 50, 60,000 feet into the atmosphere. So we take the radar and we scan it starting at the surface. And every time it goes around, we move the antenna up a little bit more in elevation. And how we do this is called the radar's volume coverage pattern. And we have various volume coverage patterns, or VCPs, that we use on the radar. For what we call precipitation VCPs there on the top right, we have different numbers. I don't expect you to memorize the numbers, but they can scan the atmosphere in about 4 to 6 minutes. Whereas the clear air VCPs here on the bottom, you notice they don't go up as high in the atmosphere, but we don't need to because we're looking for, say, snow or drizzle. Doesn't go 30, 40,000 feet into the atmosphere, so we don't need to look that high. And you'll notice that, we don't go all the way up to 90 degrees. And this is just a limitation of the elevation motor. And so this area above the radar is called the cone of silence. For those of you who ever watched the movie Twister back in the 90s, Dusty loved the term cone of silence. This is actually what cone of silence means. It's not what he used it for. So, even though it sounded really cool when he used it, trust me. The adaptation scanning strategies, this is what we really worked on improving over the last decade with the 88D. So what happened when the 88D was deployed, we started at our space degree, we went all the way up to 19.5 degrees, which was the top of the scanning strategy, and then went back and started again. And that's how we scan the atmosphere with the radar. But we decided that's really not the best way to use the radar, because Mother Nature doesn't always give us, a storm in the perfect spot to sample it. So what we started doing when I started in the Weather Service, we installed or built the AVSET algorithm into the radar, which basically looks and says, well, hey, if there's no echoes above here, why am I looking all the way up to 19.5 degrees when I could just start over again and look, again, starting at the surface. So this was really meant for storms far away from the radar. You don't need to scan all the way up to 19.5 degrees because, let's say, by 6 degrees, you've already overshot the top of the storm. You don't need to look any farther. Let's start over and look again. So that helps improve the speed of the radar there. Sales was a big game changer, which started in, again, 2014-ish. And this allowed us to, instead of, starting at half degree and going up, we could insert additional low-level cuts within that volume scan. So the radar would go up a little bit, and then it would go back down, scan again, go back up, scan a little bit more, go back down. So the radar motor gets a lot more work, obviously, doing this. But we get those low-level cuts, which are critical for looking for tornadoes. Instead of once every 5 to 6 minutes, we can get them into as little as 1 minute. So which really helps speed up the radar for those low-level cuts. And we also added another scanning strategy called MERL, which helps us find tornadoes closer to the radar, because sometimes you might undershoot the tornado if it's too close to the radar. So you might want to scan those lower 3 or 4 cuts versus just the lowest cut, which is what Merle was designed to do. And then the MPDA, again, I'm throwing acronyms at you, please don't memorize these, was designed to basically combine 2 velocity images. So remember how we said we were taking 1 scan for the range, 1 scan for velocity. Now with this algorithm, we take 2 scans for velocity and we change the PRF. So we start at 1 PRF, scan, go to the other end of the PRF spectrum, scan it again, and then merge that data together. So we get rid of that ring I showed you in the images, and I'll maybe show an example here on that later. So it's a lot to memorize, and this was a cheat sheet I made for us at the office here about, when to use your PRFs. And again, we have them by numbers, but trade-off is basically you can trade off your sensitivity versus speed depending on the PRF you want to use, where if you want higher sensitivity to find that snow and that drizzle, you go to the long pulse mode, which is the PRFs, which is VCPs 31, 34. Or if you want to move all the way to the other end of the spectrum, they can be VCP 212 and 12. And again, don't ask me why they assign numbers like this. I wasn't there when they did this, but this is the numbers that they use for this nomenclature. So the radar is far from perfect. We have many limitations we have to overcome with the radar. The first and probably the most obvious is beam height, because the radio wave energy, when it's emitted, generally goes out in a straight line. I say generally, I'll show why. But because the Earth curves away faster than the radio wave energy does, the beam increases with height as we go away from the radar. So as the storm moves farther away, you're not going to see the lowest levels of the storm. And then there's beam propagation, which is a whole different nastiness in and of itself, because the atmosphere, we get all sorts of fun echoes off of that. And this is a great example on the right-hand side when I worked in Des Moines. This is actually a clear night. This is actually a clear night. There's no clouds in the sky. Every one of those echoes is a wind farm. And I'm seeing wind farms 200, 300 miles away from the radar. That radio wave energy is supposed to be somewhere around 15 to 20,000 feet above the ground. And you can see it's not there. So this is a great example of ducting, where we're just hitting wind farms all over the place across the state of Iowa, where the beam should have been way, way, way higher. Another thing, this is a great example. If you had a flashlight and we're shining up against a wall, the beam stays concentrated when it leaves the flashlight, but as it leaves, it broadens and becomes more diffuse as it goes away from this flashlight. And the same thing happens with our radio wave energy. So this is another example here where as the beam energy travels farther, it takes a stronger storm to show up as the same signal on the radar scope. So the example here on the right side, this is very close to the radar. You can see great detail. The storms show up quite well, but as you go farther away from the radar there on the bottom right, you see it kind of gets smooth. The detail isn't quite there anymore. So that's another limitation we have to factor into when we're looking at radar data. And this is one of my favorite slides, where I talked about the different bands of the radar is. And we have an S-band radar, where the wavelength falls generally between 8 and 15 centimeters as your S-band. And what's great about S-band is, of course, you can be able to go through rain relatively easily and not have attenuation where the signal becomes overcome and we can't see what's beyond that rain. Now, the downside of these S-band radars is they need to be massive. As I said, we have a 28-foot wide dish we're trying to work with here. And for a lot of, say, TV stations who have their own radar, they don't have the money or the footprint to support a radar like that. So they often go down to what's called a C-band or even an X-band radar. The problem is as you decrease the wavelength, the attenuation really starts to ramp up on these radars. So this was an example I took when I was at Des Moines. The TV station down there had a C-band radar, roughly located near where our radar was at Des Moines. And so the C-band radar is on the left, our S-band radar is on the right. And you'll notice very quickly, all the echoes you see here in northern Iowa don't really show up there at all north of Ames at all. This is because we have so much attenuation going on just south of Ames, is those echoes that you see with our S-band radar really don't show up at all. And in fact, all these storms developing down here east of Omaha are non-existent on the C-band radar at all. Simply because, again, so much attenuation was happened, all the radio wave energy was reflected back to the receiver on the C-band radar. Other issues we deal with are side lobes. We don't emit a perfect radio wave pulse. The radio wave energy kind of just is blasted out there, but we try to concentrate it as best as possible. But we still get these side lobing that happens. And when you're trying to take a three-dimensional cross-section of a storm, this bottom center image here is a real great example of, the storms sometimes have tilt to it. So you're sampling underneath the storm, and suddenly you'll get these really bogus echoes because we're hitting a side lobe that was higher up into the atmosphere. And the radar thought, whoa, it's supposed to be 10,000 feet lower than it actually is. And it actually is not there. So side lobing is something we have to take into consideration. And then finally, scatterer concentrations is the radar is only able to see particles that it can bounce radio wave energy off of, which are generally dust particles or raindrops. If there's no particles there for us to sample, we can't see those parts of the storm. And so there's a whole different part of the storm called the updraft or the inflow region, which we sometimes just can't sample with radar because there's no raindrops there. So that's something we need to consider as well as, radars can only see certain parts of the storm, and we have to kind of mentally bridge that and build our mental picture about what the storm is looking at, what the radar is looking at. So the main products that we produce with the WSR-88D, the one that you probably see every night on the TV screen, is called reflectivity. We measure it in dBz. It's a simple calculation of the amount of radio wave energy that's backscattered to the receiver. And it's not just a matter of size of what the radio wave energy is intercepting. The amount of radio wave energy that comes back could be a function of the shape of the object, whether it's round or flat. The state, again, the state is actually a very big, whether it's liquid or frozen or mixed. Mixed can be a real fun one. And then also concentration. All of that plays into what the signal sent back to the radar looks like. So it's not just a matter of, well, I have a really high value there, it must be raining really hard. You can have high reflectivity from just a small amount of big raindrops, and it will look the same as a lot of little raindrops. So that's where dual pol really helps shine the light on that later on. But, we also have to contend with the fact that we have to deal with different scattering properties here with the radar. Rayleigh versus Meuse scattering is something we have to contend with a lot with, where the target diameter, once you get above a certain point, the amount of radio wave energy scattered back from a given target, as it increases in size, eventually you're going to start having a nonlinear reflection of the radio wave energy back to the receiver. And when you transition between that, we have what's called Meuse scattering. And with the 88D, Meuse scattering starts to happen when a target diameter exceeds roughly 1/4 of an inch. So all of these big hailstones that you see with the radar sometimes actually have really low reflectivity values because of that Meuse scattering that's happening. And a lot of times the highest reflectivity values we see are when we have really small water-coated hailstones. So when you see these big areas where the TV Met's like, well, look, we have 60 to 70 dBz here, that must be some big hail. Not really always. That can be a big of a stretch. So a lot of times that's where we take that three-dimensional look at the storm and see how deep do those higher reflectivity values extend, and we can then transpose it to our knowledge of how cold is it up there, where should the storm be generating that hail, and be able to build a better picture of what size hail we're looking at. So it's not just a simple function of reflectivity. With reflectivity, again, we're able to look at storm structure with these, identify boundaries between colder and warmer air masses, but it's really not meant for, diagnosing wind or hail size, and certainly not tornado. Now, they used to look for the old hook echo way back in the day, and that was really the only product we had was reflectivity back in the day, but there's really a lot better ways for looking for tornadoes than simply looking at reflectivity. With velocity, velocity is simply a shift in the radio wave energy along the radial, but the key thing to remember here is the radar can only sample a one-dimensional look at the wind field for what is really a three-dimensional wind field. So we, again, have to try to build that mental picture of what should the wind be doing, and be able to use that to diagnose storm structure. So this one-dimensional look at the velocity pattern can be especially problematic, like say if you have a line of storms that's moving parallel to a radar beam. So if your radar beam is shooting like this, your storms are moving like this, and the wind is all going in this direction, there's nothing for the radio wave energy to actually intercept or be shifted by because it's completely orthogonal. So that's something we have to contend with. So you'll see storms that are, when they're or when the wind pattern is orthogonal to the radar beam, it'll show up as almost zero for velocity. Sometimes we want to switch from an Eulerian to a Lagrangian look at these storms, and so we subtract the storm motion from that, so we're able to sample rotations better. Again, looking at how the airflow is moving through the storm, we'll subtract out the storm motion to get a better look at that. Great for looking for tornadoes, but obviously you want to be careful in doing that and not look for, say, the wind strength, because it's not going to be what's sampling at the ground. And then we're also able to look at a product called spectrum width, which measures the variability of that wind value in a given what's known as a range gate, because we're sampling those areas of the atmosphere dozens of times as the radar beam's moving through its sweep. And so if we're getting a lot of variability in those wind measurements and those velocity measurements, we can plot that out there, and we can infer turbulence, we can infer rotations out of these boundaries, lots of cool stuff. But that's not a product your TV Met's going to probably ever show you on the TV screen, that's for sure. Now shifting gears, the last three products, these big products, this is one of the dual pole products, is differential reflectivity, which is simply a difference between the horizontal and the vertical pulse, the reflectivity value pulse. And so it's measured in dB. And when you have positive differential reflectivity values, you have more of an object in the horizontal orientation. If they're near zero, you have something that's spherical. If you have something that's negative, you have something oriented in the vertical. And vertical doesn't happen very often. You tend to see that with, say, ice crystals. Those tend to be oriented in the vertical. Sometimes you see it with snowflakes. But they're really good for locating hail cores, because those hailstones tumble and they show up as near zero, even though they're not really circular, but they tumble, and the radar sees this near 0 dB signal, able to diagnose heavy rainfall. Ice crystal structures, again, this is what differential reflectivity is really great for. Another useful product that you may have seen on TV is called correlation coefficient, which is, again, we're sampling a given volume of the atmosphere dozens of times as the radar is sweeping around. And based on the homogeneity of that signal, we can then plot that on the radar scope. So if you have particles that are all the same size, you're going to have basically a correlation coefficient near 1. And as that homogeneity decreases, your correlation coefficient will likewise decrease. And this is really great for identifying debris being lofted by tornadoes. It shows up incredibly well. Other things, large hail, ground clutter, where we basically have non-meteorological signals showing up on the radar that kind of look like rain, but we can identify it because they have correlation coefficients that are really, really low. And the last big product we use is called differential phase shift, which is, again, measuring the differences between the horizontal and vertical wave phases. Because what happens is, as those radio waves are going through liquid, they'll slow down just a little bit. And we can measure how much that slowness occurs and able to see how much the phase shift happens, and be able to basically come up with the liquid content of a volume. And so this is useful mainly for identifying heavy rainfall locations where you have really high values of KDP. So in this example, this is where I said, if you have really high values of reflectivity, you might think, oh my gosh, we have really large hail here. But your KDP values are really high. It means you have a liquid content. You don't have ice. It's not hail. So this is actually where you have really heavy rainfall or really small water-coated hailstones, which are incredibly reflective to the radar. And your KDP will help be able to diagnose between that hail and heavy rain signal. We talked about the different products here. Mainly, the radar produces 3 different levels of products. The first one is the raw radio wave energy. We don't actually see that in the office. That gets processed by the radar system, which is produced into the level 2 product stream, which is the reflectivity, velocity, and so forth. And then we can derive even more products off of that, which are known as level 3 products, which are a whole different list here. I won't go into what they all entail, but you can basically combine reflectivity, velocity, and all sorts of other products. You can figure out how high the storms are. You can figure out hail size potential, all sorts of other different algorithms that can use these different level products. And what we're also doing is, in the last 5 to 10 years, instead of looking at the storm from one radar, we try to look at the storm from our entire radar network. And we combine that with model data and look at it from really a whole different viewpoint. And this is known as the multi-radar, multi-sensor suite. And what we can really derive off of that are really, it's incredible what you can come up with, in that you can look at the storm and you can factor in, if you have a storm too close to the radar and it's in that cone of silence, the MRMS will take that over and be able to use a neighboring radar right away to help figure out the storm characteristics and be able to alleviate that cone of silence. The hail algorithms are much better with the MRMS versus our single radar network or single radar looks. And it's really neat that you can actually then develop, these temporal swaths and say hail size. You can look at rotation tracks that span states instead of just a single radar scope. You can look at it from all the radars and see how that rotation is changing. So it's really neat how that's helped us in operations. But again, there's always pros and cons to each. Because it takes time to reprocess this data, the MRMS data is a couple minutes slower than the raw data as it comes into our system. It's also a bit more smooth and a bit blockier, and the resolution isn't quite as good as the 88D, simply from all that merging of the data together. The product resolution isn't as good. But again, being able to take the collective input of all the radars to just one single answer is a lot easier. I remember having to look at 5 different scopes and try to piece the storm together in my head, and now with MRMS it's a whole lot easier to do that. Really neat stuff. So when it comes to radar interrogation, we talked about the products. How do we use it for severe weather interrogation? So with tornadoes, as this is why we have the radar network in the first place, is for tornadoes. Is a lot of the research has shown that tornadoes form from near the surface and then form upward. They don't touch down really per se, even though they kind of look like it. It's the visible funnel that we see coming down, the visible condensation funnel that comes down. And really, tornado genesis happens very close to the surface and then expands upward as it merges up with the deeper rotation in the storm, which is known as the mesocyclone. So you're like, well, shoot, usually the radar beam is sitting up here and the tornado is forming down here. How the heck do we see tornadoes then? We still use the radar, and the radar is our best tool really to help identify what features and functions of the storm are contributing to or even amplifying the potential for a tornado to form. So we're still looking for rotation in a storm. When we say radar indicated rotation, we're still looking at that in the storm. The storm usually has that deeper rotation that helps develop the tornado. It helps get everything in place for the tornado to form at the surface. So we're monitoring to see how that rotation is behaving. Is it descending in the storm? Is it getting closer to the surface to help kind of draw that near surface rotation upward and connect with it? Is, of course, the strength increasing, or is it actually contracting and amplifying? As think of like a figure skater, as he or she spins and brings their arms in, they spin faster and faster. If that circulation is contracting, the same thing can happen here, and you can have more upward motion underneath the storm. We do look at reflectivity a little bit still for the development of that hook echo. It's still a valid feature, but it's also, we see a lot of those many of those that do not produce tornadoes. So we still look for those to be present in certain storm modes. Obviously, strengthening low-level vorticity couplets. You can see from here, we don't have much of a signal on velocity, and 10 minutes later, it really amplifies up. So again, we're looking for that rotation near the surface to help give us clues that a tornado is about to occur. When it comes to tornadoes, Mother Nature doesn't throw us one simple supercell thunderstorm and say that's how you get tornadoes. Tornadoes come from all sorts of different types of storms. We sometimes have to deal with what are known as low-top supercells, where instead of the storm going up to, say, 50,000 feet, it goes to about 15,000 feet. So everything gets compressed, and suddenly a storm far away from the radar, you basically just shoot over the top of it and you can't see it. So we have to contend with that sometimes and adjust our thinking for what tornado potential is possible with those. High precipitation supercells, the circulation then moves to the front of the storm instead of the back. So you kind of have to adjust your mental thinking there of where the tornado might be. And then even low precipitation supercells, where, as I said, if you don't have rain to sample a circulation, you're not going to see it. So in those instances, that back edge of the storm, that rear flank downdraft, where it's key for looking for the rotation, suddenly is devoid of echoes, and you can't see it very well at all. So we have to deal with all those different storm modes for trying to figure out tornado potential. And then, of course, there's squall line tornadoes, which are just a beast in and of themselves. The tornadoes are embedded within this line of storms. They develop in the rain. They're basically impossible for spotters to see. They're oftentimes generally short-lived, and the circulation, you don't have a bigger deeper circulation above it to give you clues that something's about to happen. These circulations just pop up out of nowhere. So you got to really look for clues on how the orientation of the line is changing and environmental clues to really hone in on where a tornado might be occurring. So in this instance, you might be looking here on the line, and further down here is areas where a tornado might be getting ready to occur. And then there's land spout tornadoes. Have you guys ever heard of land spout tornadoes before? Maybe a couple of you. These are really no fun to warn on whatsoever. I would use naughtier words if I wasn't being recorded. Because what happens is these type of tornadoes form when a storm is basically in its incipient development stage, or you basically have cumulus clouds overhead, and you have a really strong circulation or what we call baroclinic zone at the surface, where you have a boundary or a front just sitting there, and you get these little eddies that form there at the surface, and the cumulus clouds goes over them and whoop, stretches it up to a tornado real quick. But because there's no rain, it's invisible on the radar. So that's where we rely on spotters to help us out. But thankfully, land spouts tend to be really weak and really short-lived. Think of them as really glorified dust devils that just happen to technically meet the definition of a tornado. Dust devils are kind of like your baby NATOs, and land spouts are just one step above that in terms of that. Again, we talked about tornadic debris signatures a little bit with correlation coefficient. So in this case, if you have a strong velocity couplet in this example, you can see that circular region of lower correlation coefficient right here. That's your debris being lofted by the tornado up into the radar beam that we can then see. And it also, because of that tumbling motion, the differential reflectivity goes down to near zero or even negative inside that tornadic debris signature. When it comes to hail interrogation, as I said, we look for that where those higher reflectivity values are in the storm and look for other signals in the dual pole data to try to figure out what type of particles we're looking at in the storm. So we're looking for that large, deep area of higher reflectivity values above the freezing level, not just at the surface. We're looking to see where the hail is being generated aloft in the storm, which is why that volumetric look at the storm is so important for hail detection. Other signals we look at, we look to see how the storm is tilted. We look to see if we can see signals for a really strong updraft. And I don't know why that popped up. We look to see, we sometimes see these features here on the bottom left here. This is really neat, called a three-body scatter spike, where the radio wave energy hits the hail, bounces down to the surface, bounces back up and hits the hailstone and comes back to the radar. So we get these elongated spikes that show up down radial from the radar. And these can be really impressive. They can, that hailstorm we had down in Iowa and southwest Wisconsin last week had a really large three-body scatter spike on it. It was really impressive. Other things we look at, those rotating storms, those mesocyclones can help hold the hailstones longer and allow them to grow larger. We also look to see at the bottom right here, how much is that storm venting? How much is the air rising up to the storm? We look to see how the air is diverging at the top of the storm. And the more it's diverging, you can basically imply the faster that updraft is. Because remember, the radio wave energy, if the storm is going up, if the air is rising up, we can't sample that velocity. But we can sample it when it comes out the top as it diverges. So we can then infer updraft strength by the top of the storm. For damaging winds, obviously, if the storm is coming right at the radar, we could see high velocity values. That's the easy slam dunk signal. But oftentimes we don't have that luxury. We have to look to see, where is the air descending? We look to see bowing structures and the reflectivity here on the top right. This is a great example of where you have that bow echo, you may have heard of it called. This featured on the backside here, that kind of V-shaped notch in the reflectivity is called a rear inflow jet. And that could basically be a really strong surge of air on the backside that gets funneled in right to the surface and hits the surface and can cause winds of 70, 80, 100 miles an hour very quickly. Again, all of these are signals we're looking at on the radar to help diagnose what the damaging wind threat is. So we're not just looking at the velocity values, we're looking to see other signals that the storm is giving us to help us diagnose those winds. And of course, radar, winter precipitation isn't nearly as cool, but we can certainly use radar for that nature. We can look to see wet snow versus dry snow. With wet snow, you tend to get more clumping of the snowflakes together. It's called aggregation. And that will lower your correlation coefficient a little bit because you have different sized particles. So we use that for both for winter and for snow. But the coolest feature we can probably see in the wintertime is called the melting layer, where if you have warmer air at the surface and colder air aloft, as those snowflakes are coming through and they hit that warm layer, they start to melt before they transition to rain. And that melting causes a ring to form in the radar scope. And this is a great example of that ring. We could see it in reflectivity, but it really shows up in correlation coefficient, where you have snow up here above the radar scope, and as you move towards the surface, it melts right here, and this is the melting layer, and below it is actually rain. So that's where we can help diagnose precipitation type with radar. Really neat stuff. We can also have to deal with non-meteorological targets. We can deal with antenna interference from, say, cell phone towers. We can deal with that at times. You can see those spikes right there. Sometimes we can actually see birds taking off with the radar. We can see those a lot here in the spring and the fall during the migration season, especially get towards the Mississippi River. You can see these rings that show up at sunrise as all the birds are taking off, all from all their roosts. It shows up really cool here on radar. Chaff. If the military is out there and they want to do some exercises and they drop a bunch of chaff over their radar scope, well, this is what it looks like. All of these long linear streaks you see right here on the radar scope, this is all chaff. There's actually other weather echoes embedded here, but all these streaks right here are chaff. You use the dual pole products to help kind of separate the chaff from the weather echoes, because chaff just looks like garbage on this correlation coefficient product. We try to remove clutter close to the radar, especially with our radar located in the cross. Sometimes we're hitting the tops of those ridges with our radio wave energy, and sometimes that can actually filter out echoes we want to see on the radar scope. This is an example here on this oval. You can see it goes from really high to really low reflectivity values in very short order. And this is just bad data clutter filtering. And even sometimes, it doesn't happen very often, but we can sometimes get another radar's energy and hit it to the wrong receiver. And this is called bistatic coupling. This is an example here where the echoes are just messed up completely from another radar. I think this is the Raleigh radar, and I think it's getting energy from, I don't know, Atlanta radar or something like that down on the East Coast. I don't know exactly where that is. So wrapping things up here, the big question is, what is the future of the WSR-88D now that it's 35 years old? When it was built, its life expectancy was about 25 years. We're past that now. What we did starting in the mid-2000s is we went through about 4 different what are called service life extension products, or SLEPs. These were all completed over the course of a decade, ending last year, where we took apart every part of the radar that moves and replaces it, and some parts that don't move. We replaced all the equipment shelters at the base of the radar. We replaced the backup generators. We also replaced the signal processor units. And the big one was replacing the pedestal, because to replace the antenna pedestal, you had to take the radome off and take the radar apart. So that radars were all down for about 2 weeks. Each radar was, as we took the radome off and took the radar down and replaced the pedestal and put it all back together. So the 88D that you see now has a lot of new parts that weren't there when it was deployed in the 90s. And this was really to ensure the network is reliable beyond 2035. And probably will still be there when I retire in 25 years, honestly. So really, what does the future hold for the Weather Service network, radar network in general? There's the phased array radar network, which is a solid state dish, doesn't move, doesn't have moving parts. The big thing obviously with these is they are prohibitively expensive. I think one of these costs, I don't know what the number is. Was it $40–50 million? You times that by 120, 130 radars you want to deploy across the country, that bill becomes very large very quickly. And the phased array doesn't solve some of those basic radar problems that we have. Yes, it can scan a full volume very quickly, but as far as the range problem goes and our velocity, the Doppler dilemma, you're still not solving that. So, is phased array the answer? Maybe in the long range future. But again, it's a big lift from a monetary standpoint when your gain may be not quite there. So the future might be more of a hybrid network where you have either the 88Ds or a phased array radar, and then with smaller C-band or even X-band radars to kind of fill those gaps between those radar networks. And we're seeing that right now. There's actually one that was deployed in southern Minnesota as a test bed last year. I don't have access to the data yet, but there was a commercial radar that was deployed west of, it was along I-90, somewhere along I-90, west of Albert Lee. To try and see what we can see with these. Now, remember, these are smaller radars. These are going to be your X-band radars, and they try to put them on top of, say, water towers. This is actually an example here of one of them. Again, they're really small, but the attenuation is really bad with these. So if you got to be looking, have nothing between you and what you want to see in order for these radars to work. So there's always a cost-benefit trade-off. These hybrid ones are really cheap to deploy, but again, they can only see 20, 30, 40 miles at best versus our WSR-88D, which can see 150 to 200 miles. So that, it's a cost trade-off there with the 88D. So that's all I had for this talk. If you guys have any questions, I'm more than happy to take them. Yes.
I have one question on the hardware.
Yeah.
Do all the locations have the same hardware? Do you have the same hardware in LaCrosse as they do in the Twin Cities or Grand Forks or Duluth?
Yep, the hardware is identical. We have a national center that reconditions this hardware. As it wears out, they'll send it back, they'll recondition it, they'll have a stockpile and send it back out. The only difference is probably going to be your tower heights, which are, again, the same parts. They're very modular in design. They just stack them on top of each other until they get to the height they want. So, yep, they're all the same. Any other questions?
We actually have two questions on YouTube here. Are the radar pulses continuous wave? Could modulated pulses carry a digital serial number to help ID the return signal?
Ooh, we're getting way into the nerd spectrum here. I don't know about that. I don't think they're continuous. Just to get a 360-degree scan with 4 panels, but those panels are so expensive that we can only afford to put one on a rotating pedestal. So you basically have a phased array 88D. Because you're still rotating, you still have the moving parts that you didn't want to have. What is phased array really giving you?
Is that what that is showing us in the bottom left there?
That's actually the phased array example from the Norman radar for one of the tornado events they had there. So as you can see, it's on that pedestal, and we're only able to sample 90 degrees at a given shot. So you can see we're trying to move the radar screw, and you can see that 90-degree wedge. That's all the radar can see right there, because they're just trying to move it and see what it can see.
And I was curious, earlier on, you talked about changing between different modes of the radar depending on weather conditions. How much of that is automated versus somebody sitting there looking at the weather and going, I need to activate this mode?
It's both. We do have automated algorithms that can sample the concentration of, we set a reflectivity threshold, and if the concentration of particles falls below that, it'll switch between long pulse and short pulse, or we call clear air versus precipitation. But I certainly have the ability to override that if I feel the need to. Sometimes, it won't switch for whatever reason. Especially it's more applicable in the wintertime when you might have the radar switch into a preset VCP when you wanted to still look at snow, because you might have that bright banding or that melting layer showing up, and it trips it into preset mode, and you suddenly you can't see the snow over here in Rochester anymore. So you keep it over in long pulse mode for longer.
Kind of an extension to that question. Yeah. When you've got one of these storm events and you're looking at all these images, you mentioned a whole bunch of stuff you're looking for. Are you doing that all manually yourself, or do you have image processing software that's helping you, do some of that, or how does that work? So we look at the radar data through a number of different ways. And we have our system at the office, which is known as AWIPS, which stands for the Advanced Weather Interactive Processing System. Don't memorize that. So I can slice and dice the radar as many ways as I want. I have procedures that I can look at every single image, every single scan in one screen. Now, obviously that's a lot. I don't want to look at that all at once. So what sometimes we'll do is we'll load what are called all tilt, so we can use the mouse and arrow keys to look up and down on the storm very quickly. But again, this is where that MRMS product really comes into play. So I can then, instead of looking at 18 different images to try to find one answer, I let the computer system do that. But I still have it as the backup because, again, you can see things in there that the computer system might think is garbage. Like, for example, those 3-body scatter spikes. The computer system thinks that's interference and tries to remove it, when that's actually a signal you really want to see. So the answer is it depends. Both.
It's both.
When you talked about the different patterns you look at to recognize the storms, various storms and tornadoes, for Midwest here is a way, and then if you go down to Tornado Alley down in Texas and that, they have a whole different set of patterns they look for their storms down that way.
That really depends on the environments. This is where we look at, what
is driving the storms? What is the weather system doing? You know, what is the temperature, dew point spread at the surface? What is your wind shear? What is your instability profiles look at? What is the storm mode? That drives a lot of what we're thinking of. Where should the tornadoes be? How strong will they look at the radar? I mean, if I'm dealing with a supercell, I'm going to see a beautiful rotation signature, where if I'm dealing with a squall line, it might not show up at all. Your first indication that a tornado is happening might be the debris coming up through the radar scope, and you're like, uh-oh, you don't like that. So you really have to put your mindset into what the environment's doing and how that's driving your storms and your tornado potential.
Talked about how the different bands, as you go down in wavelengths, have shorter ranges.
Mhm.
Is there any radars that are trying to go longer in wavelength to go further out?
Well, again, there's the cost benefit there of, even if you go farther out, you're still dealing with beam broadening, beam height. The 88Ds, as they learned over time, are kind of that best of both worlds, where you get the range where at the edge of the scope, you're probably at 15, 20,000 feet above the ground. You're not going to get any more useful data beyond that point. Because again, if you go with a larger wavelength, your antenna size has to increase. It's really big. We're talking like, these are like the deep space radars you hear about. They have antennas that are hundreds of feet wide, and you don't want to try to move that around on a pedestal. So the 88Ds, they learned, this was what they learned back in the 40s, 50s, and 60s, is that's kind of your sweet spot of that S-band, roughly, for getting the best range, best bang for your buck, essentially.
And you mentioned that you're using hundreds of kilowatts for powering that thing?
650 to 750 kilowatts. Our electric bill for one radar for 1 month is $10,000. Yeah. For one radar for 1 month, it's $10,000.
Have a massive substation nearby then.
Not really.
Oh.
Well, if you think about it, it's all that's, you spread that out over the radar is always on. So you spread that power load out over the course of the entire month. It's actually not nearly as bad as it might seem.
Do you have a feel for how the American system rates compared to, would the Europeans have a better system, a newer system, or we have a state-of-the-art system?
We've been fortunate enough to keep upgrading it. With the European system, again, it's each country kind of develops their own a little bit. I would still say our coverage is probably the best in the world. And I think that's what matters most. It's not a matter of, who has the prettiest hardware. It's a matter of what can you see with it. And I think ours is still top of the line. The Canadian network, they have a great coverage in the very southern tier along our border, but as soon as you go north, you can't see butt kiss because there's no radars. Kind of like our Alaska radar network. It's only there in the population centers, but as soon as you get outside of that, can't see a thing. You rely on satellite more often than not. Any other questions? Yes.
Our local TV station here, just on the north side of town, has a radar dome. Does that interfere with yours, or just supplement yours, or what's going on?
If it's the TV station, I think I don't remember the call sign. Which one was it? WWL or which one it was? KTTC. Because I was just talking to someone over there. They had a tower and they just took it down. That was an old C-band radar, so that wouldn't interfere with ours at all. Because we're at an S-band frequency, so theirs is a C-band. Theirs was a C-band. They last ran it in 2012. They just took it down a couple months ago. Yes.
So they're all relying on information from you.
There's no local radars down here in Rochester. There might be still one in the Twin Cities. I don't know if CCO still runs a local radar or not. I don't know which ones in the cities have their local radars anymore, but the vast majority, when you see radar images of the entire Midwest, that's our radar network. No one has their own radar network that covers that range. Anybody else?
Thank you.
You're welcome.